log functions. We're going to basically start with everything we know about exponential. Only the table that we start with really changes. Of course, the whole shape of the graph will change also. You're going to know it's a log question because it says log in the question. Great. So same first question, what's the base? 2. That tells you what table to start with. So let me show you an optional step. So we're going back to notes. This is number 3. An optional step would be for you to make the table for 2 to the x first. And then you can switch the x and the y's. So if that helps your brain, do that. If you don't need that first step and you can just say, okay, I'm ready to tackle this log base 2 because I know that the y's are -1, 0, 1, and then the x's are 1/2, 1, and 2. So this part over here is just optional if it helps you to have the visual of the exponential one and then switch it. Or if you just know, hey, log is the inverse. The -1, 0, 1 will be the y's this time. We still have an asymptote, but now it's vertical. So you're going to have to put x equals 0, and we're going to have to use the x changes, the horizontal changes of our table, to figure out what that new asymptote is. Okay, so that's our starting table. Now let's look at the transformed function. Let's start horizontally. I see inside the parentheses, this whole thing is horizontal, and I do still have to factor. So 2 times x plus 3. It separates my dilation, which here that 2 is going to be a horizontal compression. It separates it from the translation, from the shift. So I can see that I'm actually shifting left 3. So in my table, to compress those x's, now our table's looking opposite of what we actually see in the equation. 1/2 times the x to compress them, and then -3 to shift them to the left. Okay, let's, well, I guess before we plug in, what vertical changes are there? Left 3, we've got it in our x's. Are there anything like that will affect the y's? No, nothing in the front or at the end of the equation, so the y is just going to stay y. It's going to be the exact same from the parent function table, and my only work is to actually change the x's. So let's plug in, fractions again. 1/2 times 1/2 is 1/4. And 1/4 -3, you could either say, I know that's going to be -2 3/4, not quite to -3. Or you could change the 3 into 12/4 and change it back to a mixed number, as long as you can get there. That's the important part. If you'd rather do decimals, that's fine. And then plug in a 1, so 1/2 -3, -2.5. Plug in a 2, it would be 1 -3. And this is where we're going to plug in for it to see the changes to our vertical asymptote. I know I wrote it under the y. That was just a space issue, but I'm going to plug this 0 in, 0 -3. It shifts to -3 with the rest of the graph. Shifts left 3, and that's the first thing I want you to graph. So go put that boundary on there. It's a vertical asymptote because now we're graphing log functions instead. And then let's go plot those points. So negative, almost to -3 and -1. -2.5, 0. -2, 1. Very squishy with that horizontal compression. So the side that's closer to the y, or the vertical asymptote, I'm going to make it keep approaching the vertical asymptote. It follows the shape of the log graph, so it's increasing. It's increasing slowly. Okay, the asymptote we listed in the table. The domain, now it can change with a log graph because it's restricted by the vertical asymptote. So this graph only exists when x is greater than -3, or you could say from -3 to infinity. And the range, this one's not restricted in any way. All those y values are possible. Next class we'll do more practice rewriting from log to exponential, because these y's are all representing in a log, the y represents an exponent. So we could have any exponent would be valid. If that's confusing, just wait till next time. Okay, next part, number 4. What's the base?
2.
Yeah, 2. Love the excitement. Hey, y'all, it's the same starting table. So it's a log. We know that that means the y's are -1, 0, 1. Oops, I didn't save space for the asymptote. Move that. Right, it's log base 2. So since the base is 2, I know it's 1 over the base, 1, and the base. Okay, horizontal changes. Yeah, it's the weird case again. It's -x plus 4, right? I know we're going kind of fast, but we probably can. I need to factor out that negative so I can see it's a reflection over the y and a shift right 4. It's the one time where the equation has exactly what I need in my table. Then I see a vertical compression and shift up. So just do that to the y's. 1/2 y plus 3. Let's plug these values in and get this graph done. So -1/2 plus 4. Sounds like a 3.5 to me. Plug in a 1, -1 plus 4. Plug in a 2, -2 plus 4. And then don't forget to plug in your vertical asymptote with your x's, since it's x equals. It's there as a reminder. So 0 plus 4, it shifts right 4 with the rest of the graph. Now I can go do the y's. So -1/2 plus 3. Plug in a 0. Plug in a 1. Did I tell y'all yet that this is our last transformation day of the whole year? That gets a cheer. I didn't know. It was like bittersweet. Because it's always kind of a nice day when you're like, oh, we've been doing this. I've got this. It's like an easy day of the unit. But they're not the most fun things to do. So y'all, this is our last example. I mean, our last example where we actually graph it. Okay, so let's plot these points. 3.5, 2.5. Okay, woo, I'm on the left side of the vertical asymptote. Yeah, this graph, I wish it was a little bit bigger here.
2.5. Wait, yeah.
Okay, y'all, all these points are super close together because we both, we vertically compressed the graph. I guess that's it. And the fact that, like, the points were already close together, the x's to start with. So make sure, drawing it to the best of your ability. That one's a little wonky. Well, let me try it. See if I can do better. All right, I have my side getting closer to the, yeah, that's a little better. Closer to the vertical asymptote and extending this time to the left since it got reflected over the y-axis first. The vertical asymptote, we know is 4. And the domain now starts at -infinity to 4. The range will be unchanged with a log. It will always be -infinity to +infinity. So in isolation, these two tables are not difficult, exponential and log. But when I start mixing them up on the test or progress check, that's where it can get tricky. Because you have to think about what type of function is this? Does it have a vertical or horizontal asymptote? And the test is going to be all mixed up. So it's going to have an exponential question right next to a log question where we have to think about their graphs being different. Okay, y'all, last two questions we're going to do are writing equations. Write the equation of a natural log function that has been reflected over the x-axis, shifted left 3 units, horizontally compressed by 1/4, and shifted down 7. This is not one of those funky questions where we have to draw the graph and do the changes in the order it says. We're gonna make sure that our final equation would have these 4 changes from the parent function. Just normal way of doing this problem. Okay, so first thing I have to figure out, if it wants a natural log function, what is that?
Log EX.
Yes, it's a log with a base of e, which is not the way that we write it, but that's what it is. It's a log with a base of e, which we write as ln. So y equals, we are going to need an x. So I don't know, I know it'll be in here. I'm going to leave some parentheses, and let's put everything where it needs to go. So reflected over the x-axis.
Negative.
Great, a negative, so that's over the x-axis, meaning it's vertical. So a negative in the front. Shifted left 3 units. So we're going to see
X plus
an x plus 3. Horizontally compressed by 1/4.
4x plus 3. Wait.
It does need to go with the x plus 3, and it does need to be a 4, but y'all, we have to separate it. So I need to see the 4 separate from x plus 3 so that it's clearly a horizontal compression and a shift left, or you could distribute it and say 4x plus 12. That'd be fine. And down 7. What color pen? Oh, purple. I haven't used purple. Shifted down 7. Minus 7. Okay, great. So natural log meant ln, and then everything else we put in the right place. The last one says write the equation of a common log function that has been vertically compressed by 1/2 and has an asymptote of x equals 5. What's common log?
The one that we log x.
Right, it's written just as log x because it's an understood base of 10. It's that button on your calculator right next to the 7. So in our equation, we just have to write log, and it's understood that it's a base of 10. Okay, let's see. Vertically compressed by a half, we know vertical changes are outside the function. Okay, how would I make sure it has an asymptote of x equals 5?
X minus 5.
Yeah, because that would do what?
Shift right.
Yes, shift right 5. Awesome. Okay, y'all, so our test is at the end of next week. Yeah.
Can you write log 10 or would that be wrong?
Oh, good question. Y'all, can you write log 10? No, don't. It's like using bad grammar, I guess. So it doesn't show me that you understand as well. So you don't need it. Just log and then x minus 5 in parentheses. Good question.
This is the last lesson of this unit.
This is the last lesson of this unit, yes. So next week we have 2 review days before the test. There's also a progress check Monday. Review. It'll be good.